Okay, everybody, let's get started. So, all right. This terminology, I don't know what I'm going to do with y'all. Okay.
Sorry, that's red. Is that Warriors boots?
We deal with static situations in here that don't move, so I guess my speed could be fine. My acceleration is 0 right now. Okay. All right. Let's get started. Today's our last sort of pure truss analysis lecture. We're not done with truss analysis after today, though, because we're going to do deflection analysis starting Friday. And so Friday and Monday are going to be the assessment of structural deformations. And so when I used to teach this class, I would do deflections all at once, but now I'm breaking deflections up into sort of 2 parts. So we'll do truss deflections, then we'll do beam and frame deflections. And I think that works out a little bit better because like truss analysis is in our heads right now, so we don't have to like go back to truss analysis a little bit later in the semester. I'm a little bit behind again on homework grading. I said here that this homework, I thought this was going to be graded, but it's not. I'm still working on it, so sorry. But I'm hoping I can chip away at a lot of that after maybe this weekend. I'm going to give you a homework on Friday, but it's not due Monday, it's due Wednesday. So you don't have any homework in this class over the weekend. So it's almost like I did that by design. Like, I found out your materials professor is giving you an exam tomorrow, and then on Friday, you don't have a weekend homework in this class. I would like to say that's by design. It's not. It just happened to work out that way. I'm not that good. I did want to mention something, though, in case anybody's interested. I'm not teaching steel next semester. At least that's not the plan. The plan is that I'm teaching timber design, so design of wooden structures, okay? So things like glulam, sawn lumber products, things like that. It would count for the same as what happened there? Just random new presentation pops up. It would count for the same as a structural design elective, so the same as either steel or concrete, but I've never taught it before, so it'll be a fun experience. And it's never been taught here before, so.
Is someone still teaching steel, or
no? It'll just be this. So it'll just be this. So I'll teach steel next year.
Is this class the prereq for this?
Yes. So everybody in here will be able to take it. So but that would have been the same thing for steel too. So I mean. That would have mattered. But I'll say also one other thing. There's nothing to purchase with this class.
Hold on. Might be taking timber design.
What?
I might be taking timber design. I like to save money.
I'm not going to make you purchase a textbook, and we'll be able to use snippets of the code and specification that's available online. So we won't need to purchase anything. But that also means I'm coming up with the homeworks in my noggin, so there's no solutions manual that you can find online because I'm just coming up with this stuff. So
straight off the dome.
Yeah, straight off the dome. That's a good one. I'll use that one. Okay. All right. Everybody get the QR code? Okay. I kind of think lecture might end a little bit early today because we're I'll be honest, we're going to do the method of sections today, and we're going to do it because I think, like, there's no structural analysis course that is complete without addressing both the method of joints and the method of sections. But I won't deny that I don't prefer the method of sections over the method of joints. Now, I'm not saying the method of sections doesn't have its uses. It does, okay, and we're going to talk about that today. But I do think the method of joints is far more globally useful because more often than not, when we're analyzing trusses as structural engineers, we need everything, okay? We don't really have the flexibility in practice to design half the truss. We just won't worry about the other half. We'll let somebody else do it. Now, it doesn't work like that. You have to design the whole thing. You have to analyze the whole thing. If you're going to assess structural deformations, you have to analyze the whole thing. In fact, you have to analyze the whole thing twice. Okay? So there's no real way of getting around the method of joints just being more thorough. Okay? But we are going to talk about the method of sections. And why is it skipping ahead another slide? Why is it doing that? I think my pen likes me today. Okay? But we are going to discuss the method of sections today because there are some advantages to it. I don't want to totally trash it. There are some advantages. A couple things that are worth pointing out. How many of you are planning to take a 6-hour-long test next year? That is abbreviated by the term FE, right? So a very classical problem on the FE exam is, here's a truss, tell me the force in this member, okay? And doing that problem with the method of joints would just take a long time, okay? The thing about the FE exam is I don't believe the FE exam is a particularly hard exam, but it is a long one, okay? They don't ask you incredibly challenging questions, but they do ask you a lot of them. And there is a time sensitivity to the exam. And so if you're spending a lot of time utilizing the method of joints, you could just be eating up time that you could spend on other problems, right? So there is something to be said about the fact that the method of sections can be more expedient if all you're trying to do is find a force in a member that's, you know, down the way. So that's one advantage to it. Another advantage to it is that it does serve as a spot check or a gut check for some of your computations. Hopefully you should see now as you're doing your truss homeworks that if you do it right, to use a phrase from differential leveling or whatnot, or geomatics, if you do a truss analysis correctly, the truss analysis has a way of like closing at the end. Okay, and what I mean by that is, you know, the trusses that we've been doing so far, they've had an odd number of joints. Okay, and when you get to the very last joint, the answer sort of has a way of self-checking. Things like if there's only one member that you're solving for and it's a diagonal, if you solve for the vertical and the horizontal component independently, right, then the vertical and horizontal components should respect the slope ratio by default. Okay, there's ways that it should self-check. But what if that doesn't happen and you had a boo-boo in your calculation somewhere? Well, that's where the method of sections can come in. You can say, okay, let's just take the method of joints, put them over here, do the method of sections, and see if we're matching our results. So it's another tool, okay? But the other, I would say, key advantage is that the method of sections affords you another equation of equilibrium, okay? With the method of joints, we can only solve joints that have at most 2 unknown members. Now, why 2? Well, that's because the method of joints, we're dealing with concurrent force systems, all the forces all meeting at a common point. And if that is the case, there are no moments in the system. But that's not the case with a section cut. So we can cut a section through at most 3 unknown members, okay? So there's nothing stopping me from cutting a section here, looking over here, and solving for all 3 of these. I can do that with the method of sections. It allows me to solve for 3 unknowns at once as opposed to 2, okay? Now, the thing I want to clarify for everybody in the class is that when you cut a section, so we're samurai sorting or lightsabering through the truss right here, I can look at the left side of the truss or I can look at the right side of the truss. It genuinely doesn't matter in terms of the final answer. The truss doesn't care how we analyze it. The answer is the answer, okay? That's the truth, okay? The question is, just because the truss doesn't care doesn't mean we have to do more work than is necessary. Like, one of the genuine downsides of a method of sections analysis is that if you want to do your bookkeeping properly, it requires more drawing, more figures, more stuff on the page, because you have to draw the truss all over again. And so I'm lazy. So if I cut this section here, I'm going to cut the section and look to the left, not to the right. Again, it doesn't matter. The answer will be the same no matter what, but this is just less to deal with. Less truss, less drawing, less forces. So I'm lazy, okay? Does that make sense? Okay. All right. So we are going to do this problem, okay? So let me pull this up on the notepad, and let's get to it. Okay, so I'll give you all a sec to jot this down because there's a lot going on here. Okay, so I've got a truss, and we are ultimately going to solve for 3 members of the truss, And those three members are CD, CK, and JK. So I'm just taking my little highlighter and highlighting the three members. Okay. So I'll say this: I didn't explicitly tell you where to cut the section in this problem, but remember the method of sections limits you to three unknowns, and those are three unknowns. So I don't think it's really that much of a stretch to just cut the section like that. Okay. So first off, whenever I cut sections, I usually will call it like section 1-1 or section 2-2, much like you would see on a CAD drawing. Now, you might call it section AA or section BB. I usually just do it by numbers. And I guess if you wanted to use a little bit more CAD notation, maybe we'll do that. You know, I don't normally do that, but but ultimately what I'm going to do is cut a section and look this way, okay? And the reason I'm cutting a section and looking that way is just because there's less going on. I think that there's just less members I'm going to have to redraw, less that I'm going to have to handle or deal with. So I could get the same answer going the other way, but it doesn't really matter. Okay. All right. A couple other things worth mentioning. I've got loads, I've got reactions. The loads are not symmetric, so that's not a typo. This is 20 and 20, that's 30 and 30. So this reaction is just a little bit smaller than this one. This reaction is 45 kips, this reaction is 55 kips. So that's on purpose. No horizontal reactions, so that's 0. And then I did go ahead and give you the slope ratios for these two diagonal members. So that one's at a 1-to-1 because we go over 30 and up 30, and this one's at a 1-to-6 because we go over 30, but we only go up 5. So 1-to-6. Okay. Now, unfortunately, again, with the method of sections, if you want to do it properly, you're just going to have to draw this all over again. So what I'm going to do is I'm going to cut this section, and I'm going to redraw the truss looking to the left, okay? So again, my apologies for all the redraws, but it's just kind of the nature of what we're doing here. Okay, so I will try and keep that truss in view as much as I can. I'll admit, it's kind of tough writing on the really bottom part of the screen. Okay. All right. So let's do that. So bear with me, I'm going to be doing a little bit of extra drawing probably than what you see here. Okay. All right, so there's that. Okay. And we're sort of cutting the section. So this is joint A, B, C. We're sort of cutting the section like this. Okay. So what I'm going to do is I'm going to sort of imagine I'm cutting, through the truss right here. So we'll cut through like that. And then we'll sort of imagine that like the rest of the truss sort of continues on like this. Past the section cut. But really it's not there. Okay? So in other words, like this is the actual physical part of the structure, and this is what the structure would look like over here past the section cut. And I'm just drawing those lines because if we sum moments at a particular location, you'll kind of see what we're doing. Maybe we'll use them, maybe we won't, okay? All right, so I'm also going to, okay, now that we've got that, I think I'm going to scroll this down a little bit. I'm going to try something. Yep, I'm cheating a little bit. I made that a little bit bigger. So, I cheated a little bit there, my apologies. Okay, so let's start labeling this, okay? So this is joint A, this is joint I, this is joint J, this is joint K, this is D, this is C, this is B. Let's also put our loads down. This is 20. This is 20. Then there's a reaction there of 45 kips. Okay, so there's that. Okay. All right, so let's put some dimensions on here. So again, sorry, it just takes a little while to do this, and I kind of want to do it together just to make sure that we're all comfortable with what we're doing, because, I mean, you all are going to have to do this, so. Okay, so this vertical dimension is 30 feet. Each of these dimensions are 30 feet, so let's go ahead and do that. Come on. All right. Again, I spend probably a good bit of time trying to make this neat, but I really think that helps clarify what you're doing. Taking a little bit of time to make this neat really does make a big difference. Okay, so this is 30 feet, 30 feet, 30 feet. Okay, so there's that. And then the only dimensions that we're missing past this are these vertical dimensions here and here, so I'll stick those on the left. And I'm going to cheat one more time and sort of scoot this over a little bit. All right, and let me erase this. So we're going to have that dimension, that dimension, that dimension. Okay, so that's 15 feet, that's 10 feet. Okay. A lot going on there, I know. Okay. All right, so that's our section cut. Now, the one thing we have not yet identified are our unknowns. Okay? So let's do that. Okay? So one thing I'm going to do for the unknowns is I'm going to assume that they're all in tension. Okay? I find that easier from an analysis perspective when you have a lot of unknowns like this. So we'll call this CD. Okay? For the vertical and horizontal here, what I'll do is I'll put these like this. Call this CKX, CKY. JKX, JKY. And just so we're clear, that's a 1-to-1, 1-to-6. I know there's a lot going on there. That's probably the hard part. It's just all the drawing. Okay. I'll give everybody a sec to catch up. So let's put a little note over here off to the side. I'll put it down here. So all the members are assumed to be in tension, okay? And I do want to recall something with you all. It's been a while since we probably looked at this. I want to recall, here I'm going to cheat a little bit here. Recall the principle of, and we talked about this in statics, the principle of transmissibility. Okay. Whew. What is the principle of transmissibility? Because it's been a while since we talked about this. Okay. So let me explain what the principle of transmissibility is. All right. So we have a point. We have a force. Call this F, right? Now this force has a line of action. Okay? Now I'm going to bring up a cross product just once, okay? Do you remember how we defined a moment? We said R cross F. Do you remember that? What was R? Well, it was, so not quite, okay? R, in this case, was a vector that pointed like this. And it went from the point in question to this line, right? To the line of action of the force. And if you remember from statics, it does not matter if R goes from here to here, here to here, here to here, here to here, here to here. You could have R1, you could have R2, you could have R3. It doesn't matter. You will get the same moment. If you do R1 cross F, R2 cross F, R3 cross F, you'll get the same moment. Okay? Because basically what you're saying is that this force, this vector, can slide anywhere along that line of action and it will generate the same moment. Because the magnitude of that moment is the magnitude of the force times what you were saying was the shortest arm, which is the shortest distance. Okay? Now, why am I bringing that up? Okay? I'm bringing that up because what we've got is a line of action and we have vertical and horizontal components of these unknowns. I propose what we can do is slide those vertical and horizontal components anywhere along that line, okay, and it will generate the same moment. And the reason I mention that is because we're about to do that when we sum moments, and my goal for that is to eliminate as many unknowns as possible, okay? Does that make sense? Just keep that in the back of your head because we're going to do this here in a second. Now, all right, everybody good with that? Okay. Now, let's go back to what we're doing and why we're doing it. We're doing a method of sections problem. We're not doing a method of joints problem. And so what extra advantage does the method of sections gives us? The ability to sum moments, right? So I would say whenever you're doing a method of sections analysis, more often than not, the first thing that you should be considering is the summation of moments, okay? So let's talk about that. I propose that there are three, and I'll call them special, locations about which to some moments. Okay. Now I'm going to give you one. Okay? Let's start off with one. Let's start off talking about joint K. Can somebody tell me, why would you sum moments about joint K? Like, what would be the advantage of summing moments about joint K? Well, you're solving for these three members, CD, CK, and JK. And joint K is where this member and this member intersect, right? Okay? So what I propose is that if you sum moments at joint K, that eliminates those two members, right? And so that means, let's follow this through. If I were to sum moments at K, what would I be solving for if I did that?
CD.
CD. Is that right? Okay. Everybody good with that? That's fine. Here's the problem. Let's assume that I've solved for CD. What does that leave? 1, 2 verticals, 1, 2 horizontals. That's a 2 by 2 equation of system of equations. So that's just that's more work than I need to do. There's probably a way that I can do this without having to break out the 2 by 2 equation solver. Okay? So I'm going to call this, let's not do that. Okay? And the reason I'm saying not do it is because, yeah, it'll solve for CD, but then I've got 2 verticals, 2 horizontals. I don't want to do matrix math unless I have to. So let's not do that. Okay? So now, can somebody identify another joint that we could solve, or that we could sum moments at?
C.
C. That's not bad. Let's talk about C. So let's talk this through. What two members does that eliminate?
CD and CK.
So if I sum moments at C, I can solve for member JK. Then let's follow the strategy. Once I get JK figured out, what am I going to do? Sum verticals to get that, slope ratio to get that, sum horizontals to get that. No need for a 2 by 2 system of equations, right? That's a lot better. So I'm going to put myself a nice little smiley face on this one. It's like a devious smiley face. Okay. So, but just to be global here, so I've got one location that eliminates JK and CK. I've got one that eliminates CD and CK. Is there a location that eliminates CD and JK? Does that location exist?
Yeah, there's a point like 90 feet to the left of A.
Yeah, it's way over here, right? So we could go here, go here. I'll call that point X. And what I'm going to do is I'm going to call that sort of lukewarm because, I mean, that actually would be just as, like, there's no 2 by 2 equation solution. You just sort of got to figure out this distance, okay? It's not, like, that hard, okay, because this member is at a, 1 to 3, right? So if we're dropping down 15 feet, we go over 45. so that distance is 30, right? You could do that, but I don't think it's all that necessary, at least for this problem. But I'm just mentioning it because you could do it, okay? Does that make sense? It is a viable option. Okay. All right, so we're going to sum moments at C, okay? So let's sum moments at C, okay? And let's see if we can strategize this, because this isn't going to be that challenging. Okay, so we sum moments at C. Do we have to consider this 20 kips? Okay, we're going to have this 20 times 30, right, which is going to go this way. We're going to have 45 times 60 going the other way, right? Okay, so I'm going to have to do a little bit of scrolling. My apologies for that. So, okay, so this is going to be 45 times 60 and 20 times 30. Does everybody see that? Okay. Now the only thing left to figure out is an unknown. Okay, so let's scroll back up a little bit. Let's do that. Okay, so what's our unknown? Okay, so we're summing moments at C, so we don't need to consider anything for CD. We don't need to consider anything for CK. So we only have JK to consider. Okay? Remember how I said that with member J, with these forces right here, that I can take this and slide it along that line as much as I want? Okay, what I'm going to do is I'm going to take this and slide it there. Okay? Now, why am I sliding it there? Because where am I summing moments? Right here? See? The vertical component goes right through. And so all I have is a horizontal component times what moment arm?
25 feet.
25, that distance. Does that make sense? Because it's this force going this way times that moment arm. That comes right there. This is one of those reasons why I take a little bit of time to draw the figure out. It makes the problem go a lot easier. So that's going to be on this side here, JKX. 25 feet. Okay. So now we can rock and roll. Plus, okay, 45 times 60, I think that's 2,700. This is 600. So, that means, what does this mean for JK? What are we going to get for JK?
Negative 1,900.
Yeah, well, but divided by 25.
Oh,
Yeah, we got it. But you're right, it's negative.
I didn't get that.
Anybody have an answer for me on that? Negative 84. Second? Okay, so we had JKX pointing to the right, so it's actually pointing to the left. Okay. So here's this unknown, and then I'm going to go ahead and do the slope ratio right now. What's the slope ratio for JK? That's the one that's at the 1 to 6, right? So which is the smaller component, the Y or the X? The Y. So this is going to be 1/6. So this is going to be, what's a sixth of 84? What's that, 14? So that's going to be 14 kips. And what direction is that going to be? Down, because we assumed upwards, but we were wrong in that assumption. We assumed everything was in tension, but JK is in compression. So that assumption was wrong. Okay. All right. Let me scooch this over just a tad. Okay. All right. Everybody with me on that? Okay, so let's go back up to the schematic here, okay? And you all can do the bookkeeping however you want. Sometimes what I will do is I will, let me get my eraser here. I will go over here and I might say, you know what, I'm going to erase this. And I'm going to say, actually, it's going this way. So if you want to change the direction of the arrows, or you want to leave the direction of the arrows and just use negative values, either one's fine. Whatever is easiest for you from a bookkeeping standpoint. So I think that's probably fine for this. Okay. So, but just so long as we know that actually JKY is pointing down, JKX is pointing to the left. Okay. So what do we do now? Tell me the strategy. Now that we've got this solved, how do we solve for the remaining ones? What comes next? Do we sum forces in the X first or the Y first? The Y, because we only have one unknown vertically, two unknowns horizontally. So we'll sum forces in the Y direction vertically. So what do we have going up? The only thing we have going up is 45 kips and this unknown. Everything else is going down. So 20, 20, and that. So let's see what happens. So 20 and 20, and our JKY, and then this is 45, and then our unknown CKY. Then 20 and 20 is 40, plus 14 is 54. So, is CK positive? CKY, yep. So that's going to be plus 9 kips. And so that's going to point upwards because that's what we assumed, and that assumption was correct. So, what's the slope ratio for, remember, CK?
1 to 1.
So that means that the slope ratio says the CKX is also 9 kips, but it's acting to which direction? The right or the left? The right. And then summing forces in the X direction. Again, I don't like scrolling up and down as much as I have on this problem, but these problems just require a big figure. So, okay, so the only thing we have going left and right is JKX, CKX, and CD. So this is going to the left, this is going to the right, this is going to the right. Let's see what happens. So we have JKX going to the left, which is 84 kips. Then we have CKX going to the right, which is 9 kips. And CD going to the right. I think that one's pretty easy. Okay. Any questions? So what's our answer? What's our answer for this problem? Let's just do this. So we have CD, CK, and JK. Is that right? Those are our 3 members. Let's just do the simple stuff first. Is CD in tension? Is CK in tension? Yes. Is JK in tension? No. So it's going to be tension, tension, compression. So we'll call it tension, tension, tension. Now, how much is CD experiencing? That one's easy. That's just 75 kips.
Should JK be compression?
Oh, yeah, I just said it, and then I wrote a T. I literally just said it. I do make mistakes.
You're allowed what, like 5 a year?
7.
Oh.
But I'm the one keeping count, so it's a corrupt system. Yeah. I know.
No honor system in civil engineering.
What's that?
So there's no honor system in the civil engineering department.
It doesn't go well on a T-shirt. All right.
Takes up a lot of space.
What's that?
Takes up a lot of space.
Yeah, it does. Yeah. Okay. CK. How are we going to get CK? Pythagorean theorem. So it's the square root of 9 squared plus 9 squared, which is that's like 12.73. Well, you could verify that with the Casio FX 115 ES Plus or similar scientific calculator. For JK, we're just going to do 84 squared plus 14 squared. Take the root of that. And I'll go ahead and do that one for you. That one's 85.16.
Seems so easy when you do them, you know?
My goodness. What I'm getting at, though, is what I think makes these problems easy is doing the figures properly. Take the time to draw them neatly. When you rush through the figure, it will cause this stuff to be harder to follow. Like, is the distance 20? Is it 25? And then that's where the mistakes start to happen. And what I'm getting at is, I mean, it takes a long time to draw the figure, but I think your net time on the homework assignment will go down because you spend a little bit more time on the figure, you'll spend less time on that. That's what I'm getting at. Okay. Any questions? All right. So I'm giving you one section problem, and then Friday is sort of like story time. In other words, Friday we're going to spend a lot of time explaining a method. We're not going to have an in-class example. We're going to wait till Monday to do the in-class example. But Friday we're going to start virtual work. That's all I got, everybody.